So now let's consider an orange length, which is this length. Oopsie. Okay, I won't use orange, I shall use green. This green length here. Okay, because this red length actually, r delta theta, refers to these two lengths as you see on the screen. It's just that it will be different, different r values over here and here. You'll see more later on, but let's consider the green length first. So this green length is simply delta r, alright, without any, without any sort of you don't need to multiply anything. Okay, so this is just delta r. And finally, the last length we want to talk about is this one. Okay, that's quite straightforward. It's just delta z. So let's just copy and paste this thing over and place it here, and you just hit the save button. Okay, so let's do mass balance. So again, we have rho, or rather partial by partial t, rho. Okay, so this is the mass of the control volume. Okay, equals to, well, now we have the, okay, we need to consider the masses coming in. Okay, same idea as before. So you'll consider, okay, this surface. So you'll consider this surface first. So it's along these two surfaces. So what's coming in? It is rho AV. So rho, what is A? A is the area here. So that's this red line multiplied by the length of delta z. So it's r delta theta, r delta theta, delta z. So that's rho A, and then we'll use the r velocity. Okay, so this is rho times A times V. So this is the total mass flow rate. Okay, nothing too new there. It's just mass flow rate. Okay, r delta theta delta z. Okay, so this will be the mass flowing in through this surface. That's what's being done here. So we'll evaluate it at r. So VR is, just a reminder, VR is moving in this direction. So this is VR here, and then VR evaluated at r, VR evaluated at r plus delta r. Okay, so very quickly, we'll just do the same thing, but we'll need to evaluate it at r plus delta r. Okay, now z coordinates, very straightforward. So z is moving this way. That's vz moving this way. And what is the area? The area is delta r and the red line, r delta theta. Okay, so let's do very simply this. Okay, so what's the rho? We'll have a density times the area. So it's r delta theta times delta r. So delta r delta theta delta r, and we'll have a vz going in, evaluated at z. Okay, so that's the bottom one. So this is rho, this is the area, and this is the relevant velocity, similar to what we have done before. And then we'll consider the top as well. So that is simply, I'm just going to speed up now, z plus delta z. Okay, lastly, we want to consider this direction. Okay, these two surfaces. So v theta is coming in here, okay, and it's exiting here. Alright, so what's the area? Area is delta r, and this is delta z. So I'm just gonna do some simple copy pasting over here. Okay, r, okay, this is theta, this is v theta in, and the area is delta r delta z. Okay, so we'll just do the same thing. The one that's exiting is evaluated at theta plus delta theta. That's our basic mass balance. What is our control volume? What is our delta V? So we'll just look up the area of the cube. R delta theta, delta R delta Z. Excuse me. R delta theta, delta R delta Z. So that is the control volume, and I'll just replace it here. So again, we will just want to divide throughout by the volume as it was before. Okay, divide throughout by volume. Okay, so well, can we take this term out of I think I forgot this. There should be an R there. Okay, can I take these out of this derivative? Yes, I can, because this is a constant with respect to time, so I can take it out. So let's see what we can take out and what we cannot take out. Next question, can I take these three terms out? Well, delta theta and delta z we can definitely factorize out, because this doesn't vary with r. However, we need to note that r actually obviously varies with r, so we cannot take r out. We have to leave r inside. So what do I mean by that? What's the value of r here? It is r. And what is the value of r here? Is r plus delta r. So obviously r actually varies with r. So we cannot take this r out, so to speak. When it's evaluated at r and it's evaluated at r plus delta r, these are different values. Okay, so we have to leave this r on the inside. And of course, if we have a constant density, we can actually take the density out, but we'll do that kind of later. Alright, so next one, what can we take out of here? So at z, this term is constant, because none of these things actually change with z, so we can take this out. Okay, I need to put a bracket here just to make it right. Okay, so let's do just that. There you go. Simple factorization out. And again, we do it with the last one. We can take delta z, delta r out, because none of it actually varies with theta. Okay. Delete this and delete this. Okay. Now let's just divide throughout by volume since we factorize everything out. So we'll need to divide by all these three. So I'm just gonna cut, and I'm just gonna paste it under so that we don't make any kind of careless mistakes later. Okay, or at least I don't make careless mistakes. It's just to show a step-by-step thing. So same thing, let's cancel the terms. Delta R and delta theta and delta z are gone. So it's 1 on top. So it's a delta theta, delta z at the bottom. Alright, no problem there. Over here, R, delta theta, delta R will cancel. So that's 1 here. And this one here. This will cancel. 1 on top. Nothing at the bottom except R delta theta. Alright. So as usual, we take limits. So that becomes this. This one will become a derivative, okay, of this term here. Rho R VR. So okay, 1 over R, and then we'll just have this term over here. Now we see where this RVR actually comes from. RVR actually comes because we can't, R actually will vary with R, obviously. So at different values of R, this R here, this R term here will vary. So we can't take it out. So similar thing here, you just do a delta Z to, you take limits, we make the delta R, delta theta, and delta Z become limited to zero. So we'll just get this. I'll just put it this way. Okay. Okay. So the last one will be this. Oops, I should put more space here, and that will be it. Yep. Okay, so now we have our continuity equation. Let's apply constant density. Okay, we apply constant density as usual, so we can actually take all the density out. So this one will just disappear because it's constant density, so the left hand side becomes 0. So I can take rho out here, rho. Again, the density doesn't vary with z because it's constant. Rho here, and doesn't vary with theta as well. So again, rho here. Then we just divide throughout by rho. 1, 2, and 3. Now we know what our divergence operator actually looks like. Because these VR, V theta, and VZ is just this. This is our continuity equation. Okay. So in cylindrical coordinates, okay, the gradient, the nabla function or the gradient is actually like this. So in the r direction it's like this, in the theta direction it's like this, in the z direction it is like this. And of course the divergence, which is the scalar product of this, will just be simply like so. Oopsie. And just to show the derivation, the first one is VR, V theta. So I just press an enter, and that will help me to get this kind of a vector form, V, Z. Okay. So this is divergence operator in cylindrical coordinates. Okay, thanks for watching. Hope this was helpful. I'll see you guys next time. Bye bye.